How y'all doing? Anyone got any questions or need anything before we get started? All right. Today, we're going to cover a little bit more with waves. I want to talk about some stuff specifically related to sound, or just applications of the things we've been using. We're talking about some aspects of sound wave behavior that affect human sensory experience. And then this will be the last possible new thing that could be on test 2 next week. So after today, I'm cutting it before test 2, and on Friday I plan to have uploaded to Brightspace the finite list of concepts that will be on test 2, and also practice questions so that we can go over everything and make sure you guys are feeling comfortable before the test next week. Now, between today and the exam, I will cover a little bit more information. We have a lab on electricity that we're going to do, so I'm going to teach enough about electricity to be able to do that lab. I may even talk a bit about light and how it differentiates from sound. When we go over those things, information from that might be on the exam. I'm going to post a finite list of concepts for that one as well, but it won't be on test 2. So today is now the cutoff for test 2. Is that all right? After today. All right. And again, test 2 will take place during lab next week. So we have Friday and next week's lectures to make sure everyone's feeling comfortable. Any questions, remarks, needs, concerns before sound today? All right. Now, humans have 2 different categorization systems for waves. Those 2 systems being the wave's shape, is what I call it, versus the wave's structure. And each of those 2 categorization systems has 2 categories within it. I want to briefly go over those categories so that I can describe waves in terms of these things. First categorization system is what I call the shape of a wave, and this is really in reference to which axis is the wave vibrating in relation to its travel. Since waves are traveling vibrations, and therefore traveling energy, they have to move in a direction by virtue of traveling. Let's just say we're going to examine waves moving to the right, so that is the direction that their velocities point. Since waves are traveling vibrations, we categorize them based on which direction they are vibrating in relationship to the direction of this velocity vector. And there's 2 main ways we sort these things. Again, we're going to consider our velocity vectors being rightward for right now. First up, it is possible for a wave to vibrate perpendicularly to the axis of travel, and we call this a transverse wave. This is honestly the shape that most humans just assume waves take. This is how we tend to visualize waves. In this particular case, the wave is traveling to the right, and its vibrations are taking place in an axis that is perpendicular to that. Up and down is perpendicular to left and right. Therefore, this rightward traveling wave would be transverse if its vibrations were taking place up and down. Similarly, they could also take place in and out. Since the z-axis is also perpendicular to the x-axis, I just can't really draw that. But if the vibration is perpendicular to the direction of travel, we call that a transverse wave. And again, when humans visualize waves, this is usually the first thing we tend to visualize because it is pretty easy to picture. Could I get someone to hold the other end of this spring again? Thank you, appreciate it. In practice, what this would look like is, note that this wave is going to travel left to right along the spring. To create a transverse wave, I'm going to have to make the spring shake in some perpendicular axis to left and right. So up and down is perpendicular to left and right. So if I strum vertically, we get a transverse wave. But we would also get a transverse wave if I strummed in and out, because that would also be perpendicular to left and right. So this is also transverse. And if I keep shaking it, you get kind of the classic wave shape that most humans tend to think of. So that's transverse. Sound good? Now this is different to longitudinal, because we've kind of already talked about the two different axes that are perpendicular to left and right. But what happens if it is instead shaking in the same axis as travel? That is called longitudinal, and try to get this thing to stop moving. That looks a little bit different, because instead of shaking in a perpendicular axis, it's shaking in the same axis, which is a bit harder to see, but can you tell there's a difference? To cause this, what I'm doing is I'm strumming the coils left and right in the same axis as travel. And it is a different phenomenon. Humans don't tend to think about waves like this, and so they're kind of hard to draw, which is probably why we default to the transverse version if we want to picture a wave. Thank you very much. If I wanted to draw a longitudinal wave, I would kind of use the spring as my reference point, and I would show regions of bunched up coils in comparison to regions of spaced out coils. Transverse waves are longitudinal waves are basically just pressure pulses. Regions of high pressure separated by regions of low pressure. So we've got high pressure parts of the pulse spaced out by low pressure bands as well. And those pressure bands are traveling and vibrating in the same direction. They're vibrating in the same direction they're traveling in. The reason that we distinguish them between the two is it is important to note the axis of the vibration, because it kind of affects what happens. Sometimes it affects what happens when that wave hits something. Of these two types, which do you think sound is? Longitudinal. Sound is longitudinal, and we kind of need it to be longitudinal in order for us to be able to hear. This is an air cannon. And the way that, again, not a biologist, but the way that I understand the human eardrum to work is, it's basically a flat membrane like the surface of a literal drum. And when sound waves strike that drum, since the sound waves are pulsing in and out in the same axis as travel, they literally cause the membrane of your eardrum to start shaking like a drum, which coincidentally is the same thing that a speaker does. It shakes in and out like this to create the sound waves. So we kind of need sound to be longitudinal, because that is the axis that's going to make our eardrum shake. If the sound wave was doing this, it wouldn't work quite right. Does that make sense? Likewise, I can actually use this to make sound waves, or rather a pressure wave. It's not very strong, but I can use this to blast an air pressure wave at something. I can just barely make the styrofoam ball move. This is not a very strong cannon. Bungee cords be replaced. But sound is longitudinal. And we kind of need it to be, again, because that's how it makes our eardrum shake. A high frequency sound wave is just a lot more vibrations back and forth, and therefore a high frequency sound wave makes your eardrum shake more quickly, whereas a low frequency sound wave shakes less quickly. So that's wave shape. Sound good? All right. The other binary categorization system for waves is what I call wave form, or probably wave structure might be a better word for it. This talks about what the wave is physically made of. Now, all waves are traveling energy, but that energy has to travel either through something or not. To elaborate, the two types of wave structures, the way that I would call it, is you have mechanical waves that require a physical medium in order for the wave to propagate through. Any wave that requires matter, that moves through matter as a requirement, is considered a mechanical wave because it has to make some physical material mechanically move. This includes ocean waves because the water of the ocean is a physical mechanical medium that the wave propagates through. This includes earthquakes because the earth is a physical medium that shakes as the earthquake passes through it. And that includes sound, because sound requires the physical medium of the air. So, mechanical wave structure requires a physical medium. If you have no medium, you have no wave, because there's nothing to shake. And that's why you cannot hear in space where there is no medium for sound to travel through. It's just empty. Most waves are this type. Then we get to electromagnetic. These waves don't require a medium at all. And this is what light is made out of. Light is an electromagnetic wave. And that's why you can see in space, but you can't hear in space. There's no air for the sound to travel through, but the light doesn't care. Light is an electromagnetic wave that does not require a medium. That is because light is physically made out of an electric field and a magnetic field. And electricity and magnetism are able to exist independently from a medium. They just happen. They're fundamental parts of the universe. So if you create light, if you create photons, they're just kind of self-contained packets of electromagnetic energy that just exist on their own until they hit something. They don't require a medium to sustain them after they are produced. So, requires a physical medium, doesn't require a physical medium. Therefore, this type can exist in space. Which is good. We get all of our light and heat from the sun through this method. If light required a physical medium, we wouldn't get any light from the sun because the universe is empty and we'd freeze. So, you've got longitudinal versus transverse, and then separately you've got mechanical versus electromagnetic. Sound good? Questions? All right. So, combining both of these systems together, sound is mechanical longitudinal, light is electromagnetic transverse. They have opposite shapes and opposite structures. They both exhibit wave behaviors, but other than that, they're completely different. And that's why you have two different organs designed to detect them. They are both waves, so they both have frequency and wavelength and travel speed and things like that, but the mechanics of how they work are pretty different outside of those things. And that is why your eardrum is very different to the optic cells in your eyeballs. Questions so far? All right. Now, since light is literally made out of electricity and magnetism, which I haven't talked about yet, we're going to skim past this, might talk about it a little bit later, and focus on sound for right now. Because sound is made of physical air that is physically moving. That's matter in motion, which are things we have discussed. So we're going to stick with sound for today. Sound is a longitudinal mechanical wave. When it travels through air, you can think of it as basically a little pressure pulse, just kind of a traveling region of high and low pressure, and that's why it causes your eardrum to start shaking. The high pressure pushes on your drum, pushing it in. The low pressure pulls the eardrum out, and the constant back and forth of high and low pressure is what causes your eardrum to oscillate in and out. And that then gets transferred as an electrical signal into your brain. And it requires a physical medium, which for most humans, most of the time is going to be air. But sound can travel through liquids and through solids. It's just the human ear isn't really designed to hear them that way. You can get sound if your head is underwater, but because your eardrum is not built for it, everything sounds kind of funky down there. I have yet to carry a conversation successfully under the water. It's even harder to carry a conversation through solids because I can't shove my head into the dirt. But the waves do travel through there, and technically they travel faster through solids than they do through air. Air is actually kind of a really bad conductor for sound, but it's the one our ears are based on, so it's the one we stick with. Now, I want to talk today about some important factors that affect the human perception of sound and how we utilize it on planet Earth to our advantage. First up, humans that are able to hear typically hear sounds between 20 hertz to 20,000 hertz. This is the maximum frequency band that any human has ever been able to hear on record. 20 hertz being the lowest, and frankly, I think I've mentioned this briefly, but I wouldn't really even say that detecting 20 hertz sound is even hearing it, honestly, because low frequencies like that are bass tones, and I don't really hear bass. I feel it in my teeth and my bones and my lungs. We've calculated previously the wavelength of 20 hertz sound. The lower the frequency, the bigger the wavelength. 20 hertz sound has a gigantic wavelength. It makes a lot of air shake, and that's why it kind of feels like it's physically impacting you on your bigger surface area rather than your eardrum, in my opinion. You can detect it. Just feels kind of weird, in my opinion. Bless you. But it is the lowest that humans on record have been able to detect. Sounds of a frequency lower than 20 hertz are called infrasound. Infra is just a root word that means sub or beneath. So infrasound is below sound, sub-sound. It's below what a human can hear. And this is dangerous to humans because infrasound transfers energy into your body and you can't hear it to know that it's doing that. So if you are ever feeling suddenly queasy for no clear reason, leave. Because there's a non-zero chance that you're being blasted with infrasound that is making you unwell and you can't hear it. This tends to happen in caves and haunted houses. Again, a weird amount of hauntings can be attributed to infrasound making you feel unwell. If you leave the building, you start feeling better. At the opposite end of 20 hertz, we have the higher frequencies human can hear, that being 20,000 hertz. Now, most sounds that humans make and interact with aren't anywhere near 20,000 hertz. The highest noises most humans regularly deal with are like 10,000 hertz, and we just can hear higher than that. But I want to note, so that you are aware for the sake of your own ear health, that 20,000 max is probably the maximum frequency you could hear the day you were born, if even. And every second you are alive after that, that top number drops. Because every second you are alive after you are born, the cells of your eardrum are aging and losing their elasticity, meaning they aren't able to shake as fast. If If they aren't able to shake that fast, then they cannot register the higher frequency sound, and the highest frequency that you can hear constantly drops throughout your entire life. There's a link in this page to a sound frequency test if you're interested. And this just plays frequencies of sound from 0 all the way up to 20,000 hertz so that you can see what your lowest heard frequency is and what your highest heard frequency is. When I take these, I tend to cap out somewhere between 16,000 and 17,000, and that's just because I've been alive for 3 decades. You guys hopefully would cap out a little bit more than mine, given that you are younger and you should have healthier ears. But by the time you are elderly, it's entirely possible that that maximum frequency could drop to 12 to 10,000 hertz. And so as you get older, there are just some frequencies of sound you physically cannot hear anymore. And a hearing aid can't really fix that. Hearing aids help volume assistance, but not frequency loss. This, I believe, this is a personal theory of mine, but this might contribute to why you have very different music tastes to your grandparents. You can hear sounds that your grandparents can't, and if your music has those sounds in it, your grandparents aren't getting it, and therefore they aren't receiving the same experience as you. Now, there could be millions of other reasons, but that's probably a contributing factor. They literally aren't hearing the same sounds you are. And actually, both groups of people, the young and the elderly, have managed to take advantage of this particular fact. The elderly have started playing very high frequency sounds on speakers outside of like grocery stores because loitering teenagers can hear them and will be driven off by them, but adult paying customers won't, which is just warfare, which is not nice. But on the opposite end of that, I have heard cases of students making their phone ringtones super high frequency, a pitch that their teachers can't hear. So, use it to your advantage if you can.
Ooh, how do you do that?
You have to find a frequency that you can hear that people older than you can't, which you have to find your highest frequency. Take the sound test, see what that is, see the highest pitch you can hear, and then just hope that your teachers and your elders have worse hearing than you. And just for comparison's sake, this is the frequency band of dog hearing, 40 to 40,000 hertz. Dog whistles are tuned to about 30,000 hertz, which is why they can hear it and we can't. I think cats hear pretty similarly, I'm not entirely sure. But what I find interesting is that there is a very small band of low frequencies we can hear that dogs can't, 20 to 40. So if you want to make a human whistle, put it at 30 hertz. Don't know why you would, but hypothetically you can. This matters because frequency translates to what pitch of sound that you are hearing. Higher frequency is higher pitch, lower frequency is lower pitch. And the frequency of the wave correlates to how fast it makes your eardrum start shaking, which is why we lose the higher frequencies as we age. When your eardrum loses its elasticity, it can't shake as fast anymore. So take care of your ears because damaging them with too much sound can accelerate that process. Questions? Okay. Let's talk about the speed of sound, which is pretty important. We've talked about how wave speed is considered to be constant for a specific type of wave in a specific type of medium. On Earth, at room temperature, the speed of sound in air is considered to be about 343 meters per second. Just for comparison's sake, light is about 1 million times faster, maybe 0.75 million times faster, technically. And this is considered constant for all sound types and all sound volumes. Loudness and frequency don't change this number. What does change this number is if you start messing with the properties of the air itself, since the air is the thing conducting the sound back and forth. If you mess with wind speed, air temperature, or humidity, that does change this number. For comparison's sake, the speed of sound on a frigid, literally freezing day is 331, which is a whole 12 meters per second slower. And the speed of sound at boiling, so this is not summer, this is literally a pot of boiling water, is 386. So not like twice as fast, but still measurably faster. That does mean on average that sound is faster in summer than it is in winter. Summer is higher temperature and higher humidity than winter. So, changing the air's properties will change the speed of sound. Changing frequency and volume will not change speed of sound. Is that clear? Okay. For further comparison's sake, the speed of sound in water is about 5 times faster than it is in air, and that's because water is denser. It's just a better medium for conducting the sound. And in my non-biologist opinion, this is probably why there's more echolocating creatures in the sea than there are on land or in the sky. Because on land, I feel like you really only deal with bats echolocating, but in the water, pretty much every form of aquatic mammal can echolocate. You know, manatees, dolphins, whales, seals, the whole lot of them. And underwater, it's just a more useful skill. Since the sound travels faster, you get your data quicker. Also, the ocean's huge, so you really need the sound to travel faster down there. But, technically speaking, sound travels even faster through solids. Earth's crust is mostly made out of aluminum, and the speed of sound through aluminum is about 3 times faster than it is in water. Now, you can't really shove your head in the dirt and hear very well that way, but one, this is why earthquakes are dangerous, because earthquakes are just the ground shaking, and the ground transfers vibrations a lot faster than the air does. So you will feel an earthquake long before you see it coming. But humans can kind of take advantage of this. Have you ever seen in a movie a trick where someone puts their ear to the ground or to a train track and they can kind of tell if there's a train coming or a stampede coming? That's because literally the vibrations from the train or the stampede travel more quickly through the ground than they do through the air. And that also means that they reach to you sooner, and they reach you with more of their energy, more of their volume intact. So, yeah, putting your ear on the dirt, you can tell if something nearby is making the dirt shake. Again, you don't really hear through the dirt, but this is still the part of your body most sensitive to mechanical waves. So that's why you put that part of you to the ground. Now, why does all this matter if changing frequency doesn't change wave speed? The formula we've been using for wave speed up until now is wave speed equals frequency times wavelength. Well, sorry, I lost my train of thought. Wave velocity is still a velocity, and that means that the old formula works here too. V equals change in position over change in time. So even if you don't know what frequency of sound you are hearing, you can still clock how the distance it covers in a certain amount of time. And humans will use that to our advantage in some contexts. As an example, you might have heard a trick where you can count the number of seconds between seeing lightning and hearing thunder, and you can figure out how far away a storm is. if you haven't heard of that, that's what we're about to do. On a stormy night, you see a lightning bolt off in the distance, and then you hear thunder 6.4 seconds later. You ever notice that? The time it takes between seeing the lightning and hearing the thunder most of the time? That happens because of the very dramatic difference between the speed of light and the speed of sound. Light is so fast, it's basically instantaneous as far as humans are concerned. Your brain doesn't move fast enough to keep up with the speed of light. So, as soon as the bolt is made, you can basically see it in that instant as far as human processing speed is concerned. So, we're just going to consider that you saw the lightning instantly. It's not instant. Over great distances, light does have a travel time. Just for records, it takes about 1.5 seconds for light to travel from the moon to us, 8 minutes for light to travel from the sun to us, and 30 minutes for light to travel from us to Mars. We are closer to the sun than we are to Mars. But on Earth, for your human perception of light, it's basically instantaneous. So the light from the lightning will strike us instantly for the sake of this math, and 6.4 seconds after that instantaneous light, we heard the thunder. So, travel time for the sound is 6.4 seconds. Given all this information, and assuming that the speed of sound is 343 meters per second on this particular day, how far away from you did that lightning bolt strike?
Speed of the sound in the air, that's part of it.
Yes. So the sound was traveling this fast, and it took 6.4 seconds for that sound to reach you from the lightning bolt that created it. The way that thunder works is lightning happens, the lightning creates the thunder sound wave, and from its creation to you, it took it 6.4 seconds to reach you while traveling at this speed.
So are we putting it in like how far, like meters?
Not quite. Yeah, I can tell that you're on the right track, but I think you divided where you should have multiplied. Because the formula is V equals delta X over delta T. We know wave speed, we know travel time, and we want travel distance. To get delta X by itself, you have to multiply both sides by 6.4.
2,195.
Thank you very much. 2,195 meters, or about 2.2 kilometers. So, yes, you can use this trick to see how far away from you the lightning struck. If there's a big time delay between seeing the bolt and hearing the thunder, you're probably safe. It happens further away if there's more travel time. If you see the lightning and you hear the thunder immediately, hide. That implies it happened right next to you. Or close enough that the sound was instantaneous to your nervous system. is a trick that you can use. The calculation sound all right? Not intended. All right. Small related question. Would that travel time of 6.4 seconds increase or decrease on a hot, humid summer day in comparison to a standard temperature day? Decrease. Sound gets faster in the hot than in the cold. And if it's traveling more quickly, it's going to cover the same distance in less time. Make sense? So, on a summer day, the distance wouldn't change, but the time would be smaller, and therefore the speed would be bigger. Oh, and just for comparison's sake, 2.2 kilometers is about 1.4 miles. So, each second is about a quarter of a mile, 1/5 of a mile between the lightning and the thunder. Again, the more seconds between seeing and hearing, the safer you are. Now you can use this trick for a lot of things. Basically, anytime you can clock how long it takes for you to hear something, you can figure out the distance the sound travels in that amount of time. This can include something else you might have seen in a movie. Or possibly experienced if you've ever gone caving. Screaming into a cave and waiting to hear your echo. When you scream into a cave and start a stopwatch, it's going to take a certain number of seconds for your echo to travel to the back wall of the cave, bounce off, and travel back. And this happens because waves just tend to reflect off of things. Unless a surface is very specifically designed to absorb waves, waves are very likely to just bounce off of stuff. When sound does this, we call it an echo. When light does this, we call it a reflection. In fact, the only reason you can see, period, is because light bounces off of stuff. But for sound, we tend to call that an echo. And you can use the same trick with the thunder to determine the depth of the cave. Like if you listen and you clock 4 seconds between your sound and hearing the echo, that means that it took the sound 4 seconds to travel at the speed of sound from your mouth to the back of the cave and back to you. And you can figure out how deep the cave is because of that. And in movies, sometimes, rather than a cave, they'll do this into like the bottom of a pit or something. Sometimes they don't scream, they'll just drop something and they listen for when it hits the bottom. You can also, that's a slight variation of the trick. The one thing to note though, if you're using an echo rather than an original wave, is that echoes, it takes some time to reach what they bounce off of, and then it also takes some time to come back. The echo covers this distance, covers the depth of the cave, twice. It travels delta x on the way in, and then delta x again on the way back out. So that is an important thing to note if you are using reflections, echoes, as a part of this trick. Make sense? Okay. To very quickly put some sample numbers to that, you scream into a cave and you hear your echo 4 seconds later. How much time does it take the sound to travel from you to the back wall of the cave that it strikes? A little louder.
2 seconds.
2 seconds. Very good. 4 seconds is the total time out and back. 2 seconds then is the time it took to just get to the wall in the first place. So travel time from you to the back of the cave is 2 seconds, not the total 4. 4 is for both trips. And then based on whatever the speed of sound is that day, I wrote 340, we'll just assume it's cold in this cave. You can determine the distance the sound covers in that 2 seconds. So V is delta X over delta T. 340 is delta X over 2. Therefore, delta X, the back wall of the cave is about 680 meters away from you. And again, this works vertically as well if you stream into the bottom of the pit. Any animal that uses echolocation does all this math in their head. Bats are pretty smart. So are dolphins. And seals, sea lions, whales. Need some bugs, might I? Probably not. Do bugs echolocate? I don't actually know. Questions? Sorry? They definitely chirp. I just don't know if they're doing it to hear the reflection or not. That'd be something to research. But that would explain why they're doing it. I can't think of any other reason. I just want to mention some vocab words real quick. This tactic, where you emit a wave and then wait to receive the echo to determine the distance to whatever object you are shooting your waves at. There's a couple different mechanisms that use this. I said echolocation a second ago. That is called sonar, which is using sound waves. That's what the SON on the front of it means, son for sonic. Humans have built machines that do the same thing with other types of waves. Sonar uses sound, radar uses radio waves, and LiDAR uses light in order to do this. So all three of these things refer to the same basic technique, they just use different wave types in order to do it. Radar is radar. You emit radio waves at something and you wait to hear the reflection. LiDAR uses light, which I suppose is basically what your eyes are doing. Except you don't have a mechanism built in for determining distance using your eyes. I'm just going to point out sonar uses the speed of sound in order to do this, whereas both radar and LiDAR use the speed of light to do this, and that is because radio waves aren't sound waves. Radio waves are electromagnetic waves, like light. That means that radio waves travel literally at light speed, and so radar operates at the same speed as LiDAR, which is significantly faster than sonar. You can do this with these wave types. The wave speed is just gigantic, and therefore your travel times are probably going to be a lot smaller. Questions? All right. Well, that's the end of the wave math. I just want to mention a few more concepts to you guys before we break, because I just like talking about wave behaviors, I guess. First thing I want to mention is resonance. This is the notion that all objects have a frequency of sound that they like to vibrate at. This is evidenced, I feel, most clearly with tuning forks. Every object has a certain frequency that it wants to shake at, and different tuning forks are physically different sizes and different thicknesses so that they vibrate at different frequencies. And so whenever you strike the fork, it'll make a different frequency of sound based on its specific resonant frequency. But every object has a resonant frequency, and that's why every object makes slightly different noises when you hit them. But this doesn't just apply to music. It's not just what sound does something make when you hit it. Something's resonant frequency is the frequency that it wants to resonate at. Meaning if you play sound at something of its resonant frequency, it's going to start shaking. And if you keep playing that sound, the amplitude of the object's vibration is going to keep increasing until eventually that amplitude just becomes so much that the object warps beyond repair and shatters. Literally, this is high-speed camera of a wine glass being sung at by an opera singer at the resonant frequency of the glass. It starts vibrating, the glass literally starts flexing, but eventually the amplitude of the vibration just gets so much that it goes beyond what it can handle and breaks. Because every object has a resonant frequency, you can do this to anything. As long as you know that resonant frequency and are able to create it. This includes wine glasses. In movies and in video games, sometimes various villainous characters will use this to blow up people's heads. I don't know the resonant frequency of a human skull, and I don't want to know, but theoretically, that's a thing you could do. And in real life, this sort of thing destroys bridges. Has anyone seen this before? If you haven't, this is a real bridge that shook itself apart because on the day it opened, the wind started blowing at its resonant frequency. This is the Tacoma Narrows Bridge, which was built and destroyed in 1940. And because of this event, for its short life, it was nicknamed Galloping Gertie. And literally, the wind just started blowing at just the right frequency that it just started shaking and wouldn't stop. This picture here, it's a little hard to see because of the light, that's a car on the bridge's surface. And just given the size of a car, it's dipping car length down, car length up. It was very extreme. The bridge had to be evacuated. One very brave human went to that car to get a dog out of it. Both the human and the dog survived. And then minutes later, the bridge's shaking just increased to the point where it literally shook itself apart. So, people who build anything should probably be aware of the resonant frequencies of the things that they're building, and to make sure that those resonant frequencies are not ones that will be played anywhere near it, like the wind. These architects were probably fired. So, resonance is important, and this is the same as the wine glass trick. Last thing I just want to briefly mention, I've kind of hand-waved talking about volume a little bit today. Volume is the intensity of a sound, and volume does not contribute to wave speed. Volume is how big, basically the amplitude of the vibration is, not its frequency or wavelength. It is the energy that the vibration carries. The higher energy of what a sound wave is, not the faster it makes your eardrum shake, just the bigger it makes your eardrum shake. And that's why high volume sounds can blow out your eardrum. It physically makes it shake past the point it's supposed to and rips it. The way that sound volume is determined depends on how much energy is put into the sound wave and then how close you are to the source. Because when you make sound waves, you're putting energy into the air, and that energy is now spread out over basically an expanding sphere that represents the sound's pressure wave. Because when you make a sound, it's going to echo out in all directions. Literally an expanding sphere, kind of shown here. And the energy of the sound wave, the energy of the wave doesn't change as the wave travels. Instead, the wave just takes up more space. The pressure sphere takes up more space, and the wave's energy is spread out over that sphere to the point where the energy per surface area decreases over time, and therefore the further the further you are away from the sound, the weaker the sound gets, so you just can't hear it anymore. The energy just is dissipated into the surroundings of the giant energy sphere. I just want to mention, we're not going to measure them, but I just want you to be aware of the fact we tend to measure volume in units of decibels. Decibels is a logarithmic scale of base 10, meaning if something is 10 decibels louder than something else, it is 10 times louder than something else, because that's how logarithms work. Human speech is about 60 decibels. Car traffic is 70 decibels, meaning car traffic is 10 times louder than human speech. Construction is 10 times louder than that. So construction is about 100 times louder than human speech. Fireworks, millions of times louder than human speech. So take care of your ears and try to avoid decibel ratings of over 70. Questions? All right. Friday, we'll review everything you need to know for the test next week. Please have a wonderful day. Also, if you still have your Eclipse glasses and you don't want to hang on to them, I'm collecting them to donate to schools in other parts of the planet that will have eclipses this year. There's going to be one in South America in October, and you need glasses. So if you have them and don't want them, I'll take them back. You can keep them if you want them, though, souvenirs.